Legs longer than the body can afford. This organism operates with limbs that extend far beyond what its mass distribution should tolerate. Leverage increases, torque rises, structural stress compounds, and at a certain point, motion stops being sustainable. That point is past anyway. The failure never arrives. Only after that contradiction settles does the subject appear. The Japanese spider crab, a crustacean whose legs can span nearly 2 meters while its central body remains compact, armored, and deceptively small. The geometry is immediately uncomfortable because long, thin supports are inefficient in a moving system. They amplify force at the joints, they demand constant correction, and every step multiplies the energy cost required just to avoid collapse. Physics does not offer discounts for elegance. Yet this animal walks. It does not hurry because it cannot afford to. Each movement is slow, deliberate, and mechanically conservative, minimizing oscillation, keeping its center of mass low, spreading stress across joints that seem too narrow for the job. The legs are hollowed and lightweight, reducing inertia, but that creates another problem: fragility. A broken limb is not dramatic, it is expected. Autotomy, voluntary limb loss, is built into the system as a pressure release valve, a way to prevent total failure by sacrificing parts. What should be a catastrophic design flaw becomes routine maintenance. The horror is not in the loss, but in how calmly the system accepts it. Those legs also create surface area, an interface with the environment that is far larger than the body itself, increasing drag and currents, increasing exposure, increasing the chance that something, anything, will interfere. Stability should decrease with size disparity. Instead, the spider crab compensates by slowing everything down. Metabolism runs at a measured pace, tuned for cold, deep waters, where reactions happen reluctantly. Energy is rationed, not stored. There is no margin for waste. Every step costs calories that are slow to replace. Every repair takes time measured in months, not days. The legs look excessive because the body refuses to grow with them. Growth happens by extension, not thickening, pushing reach outward while keeping the core small enough to manage oxygen diffusion and internal transport without redesigning the entire circulatory plan. This is not optimization, it is containment. The crab is not powerful, it is balanced on a knife edge of sufficiency. The unsettling part is how close the system operates to mechanical failure without crossing it. There is no hidden reinforcement waiting to save it. No redundancy beyond the willingness to lose parts. When the legs move, they do so under constant constraint, never fully extending, never accelerating freely, always staying just below a threshold where vibration, fracture, or exhaustion would cascade. Seen from a distance, the animal looks oversized, almost theatrical. Up close, it feels provisional, like a structure built to last just long enough and no longer. That it can function at all is not proof of robustness. It is evidence of extreme restraint. The spider crab does not survive because its design is strong. It survives because it never asks its design to do more than the bare minimum required to remain standing. Molting without an expiration date. For most arthropods, molting is a countdown disguised as growth. Each shed exoskeleton removes protection, drains water, spikes metabolic demand, and exposes soft tissue to an environment that does not pause out of sympathy. The risk accumulates with size. Larger bodies take longer to harden, longer to stabilize, and require more calcium and energy to rebuild the shell. At some point, the cost outweighs the benefit. That point is never formally declared here. The Japanese spider crab keeps molting long after it should have stopped. There is no final shell, no terminal form that signals safety. Every molt is a controlled emergency, a temporary dismantling of the only armor the animal has. During this window, the crab is not slow by choice. It is slow by necessity. Muscles detach from the old exoskeleton and re-anchor inside a soft, collapsing body that can barely support its own weight. Water balance becomes precarious, respiration efficiency drops, and the animal must remain hidden, motionless, conserving energy while the new shell mineralizes. This process can take weeks. The paradox is not that it survives one such event, but that it repeats it across decades. The older the crab, the higher the stakes. Larger volume means more material to harden, more time spent vulnerable, more opportunity for system-wide failure. Predation is an obvious risk, but the more silent danger is internal. Molting demands precise hormonal timing, coordinated ion transport, and flawless cellular signaling. A small error can mean incomplete hardening, malformed joints, or fatal dehydration. There is no rehearsal. The body commits fully or collapses. And yet, the spider crab delays the concept of too old by simply continuing. Growth slows, intervals stretch longer, but the process does not fundamentally change. What should be an age-limited mechanism becomes a long-term survival strategy. The horror lies in the lack of closure. Most organisms trade growth for stability as they age. This one refuses the trade. It chooses repeated instability over finality. Each molt resets size constraints, allows regeneration of lost limbs, and maintains structural integrity, but only by reopening the same lethal window again and again. There is no safe plateau. Longevity here is not a reward, it is a commitment to relive the most dangerous phase of life indefinitely. The system does not age gracefully. It ages by cycling through controlled near failures, trusting that the environment will remain just permissive enough each time. The crab is not immortal, it is simply never finished. Genes that refuse to age. Normally, time is supposed to leave marks at the cellular level: replication errors, shortened telomeres, misfolded proteins, gradual loss of coordination between repair systems. In most animals, these failures accumulate until function degrades faster than it can be corrected. Here, that slope is unnervingly shallow. The Japanese spider crab does not stop aging, but its cells behave as if deterioration is an optional suggestion rather than an obligation. Growth continues slowly, tissue turnover remains orderly, and the balance between damage and repair stays near equilibrium for decades. This is not because the system is aggressive, it is because it is restrained. Cell division rates are low, metabolic throughput is conservative, and biochemical reactions occur in cold conditions that naturally reduce error frequency. DNA repair pathways are not unusually powerful, they are simply not overwhelmed. Telomere shortening, a common molecular clock, appears to proceed at a pace that aligns with the crab's slow life history, not with its absolute size. Large bodies usually demand faster turnover to maintain function. This one refuses that demand. The paradox is scale without acceleration. A massive organism running on cellular rules, closer to those of much smaller animals. The risk should be hidden accumulation, tiny defects persisting unnoticed until a threshold is crossed and multiple systems fail at once. That threshold seems perpetually deferred. Proteostasis, the maintenance of correctly folded proteins, benefits from the same sluggishness. Lower temperatures and reduced metabolic stress mean fewer misfolded structures, fewer toxic aggregates, fewer emergency responses that can spiral into self-damage. Nothing is optimized for speed. Everything is tuned to avoid urgency. From the outside, this looks like durability. Internally, it is a constant negotiation with entropy. The system survives not by resisting damage aggressively, but by generating it so slowly that repair can keep up without escalation. This creates an unsettling implication. Aging is not defeated, it is postponed by operating far below maximum capacity. There is no biological safety margin added later in life. The crab does not reinforce itself as it grows older. It simply continues to exist under the same narrow constraints that worked before, trusting that the math will hold. If conditions change, if temperature rises, if oxygen demand increases, if food becomes unpredictable, the balance would shift quickly. Longevity here is fragile. It depends on the environment remaining indifferent rather than hostile. The genes are not heroic, they are conservative. They encode a refusal to hurry, a refusal to overproduce, a refusal to burn resources quickly, even when size suggests it should. The discomfort comes from recognizing how little separates this long-lived system from collapse. It is not protected by complexity, only by slowness. Time passes, but the biology behaves as if it is barely aware of it, and that quiet denial is what keeps the organism intact far longer than expected. A crab that grows into its environment. Most animals approach adulthood as a fixed destination. Size stabilizes, internal proportions lock in, and physiology shifts from expansion to maintenance. The Japanese spider crab never fully commits to that transition. Its final dimensions are not written in advance. They are negotiated with the environment over time. Growth continues as long as resources allow, constrained less by genetics than by temperature, food availability, and the spacing of molting intervals. This creates a body plan that feels unfinished, not because it is defective, but because it is open-ended. Size becomes a record of survival rather than a preset trait. The paradox is that indefinite growth usually destabilizes biological systems. Larger bodies struggle with oxygen diffusion, nerve conduction delays, and the mechanical stress of moving mass through space. These limits are not erased here. They are sidestepped by letting growth happen outward, not inward. The central body remains compact, keeping internal transport distances manageable, while length is added through limbs that extend reach without demanding proportional increases in core volume. This reduces some constraints but sharpens others. Long appendages amplify control problems. Neural signals take longer to travel. Feedback loops lag. Precision becomes harder to maintain. Instead of compensating with faster nerves or stronger muscles, the crab slows behavior to match its hardware. Reaction time stretches. Movements become economical, almost hesitant. The environment dictates the pace. Cold water further dampens neural speed, reinforcing the same pattern. What emerges is a system that grows by agreeing to do less with more. The unsettling aspect is the lack of a stopping rule. There is no clear point where the body says enough. Each successful molt permits further extension. Each decade of survival justifies additional size. This works only because the crab never attempts to use its full physical potential. Maximum reach is rarely exploited. Maximum speed is avoided entirely. The organism lives inside a narrow operating envelope that shrinks relative to its size, but never disappears. Any push toward urgency would expose the imbalance immediately. Growth, in this context, is not progress. It is accumulation under strict behavioral self-censorship. The crab becomes large not because it is powerful, but because it remains careful for a very long time. That carefulness is not adaptive intelligence. It is enforced by physics and energy budgets. The body expands until the environment or chance interrupts the process. There is nothing in the biology that guarantees a graceful endpoint. The form simply extends, quietly testing limits that were never meant to be tested for this long. Twice a king crab, still functional. At a glance, the proportions trigger a familiar error. The body resembles a king crab scaled up incorrectly, legs elongated beyond reason, joints placed where leverage becomes a liability. The assumption follows automatically. This must be an exaggerated version of the same system. It is not. The Japanese spider crab only looks like a king crab because evolution reused a silhouette that works just well enough. Underneath, the lineage diverges, and so do the constraints. King crabs are heavily built, thick-limbed, optimized for power and crushing force. That design scales poorly. Doubling size would demand exponential increases in muscle mass, oxygen delivery, and structural reinforcement. The spider crab avoids that trap entirely. It is larger in span, not in bulk. The paradox is resemblance without equivalence. A body that signals strength but operates on austerity. The legs are not engines, they are stilts. Muscle volume is modest, movements are slow, and force output remains intentionally low. This prevents the cascading failures that would follow if the animal tried to behave like its sturdier look-alike. Still, coordination across such a wide frame remains a problem. 8 long limbs must move without interfering, without inducing torsion that could propagate into the body. Neural control scales poorly with distance. Signals weaken, delays increase, synchronization becomes fragile. Rather than accelerating signal transmission, the spider crab lowers the demand for precision. Gait patterns are simple, repetitive, and forgiving. Errors are absorbed by time, not corrected by speed. The animal can afford to be wrong briefly because it never moves fast enough for mistakes to compound. This creates an eerie efficiency. The crab looks oversized, but it behaves undersized, occupying its mass cautiously, as if aware that the frame exceeds what the control systems were meant to handle. Energy metabolism reinforces this mismatch. Large animals often burn more energy per movement simply to reposition mass. Here, energy expenditure is flattened by minimizing acceleration. The crab rarely lifts its body fully, instead shifting weight incrementally, distributing load across multiple contact points. It is less a walker than a slowly reconfiguring structure. The horror is subtle. The system works, but only under strict self-imposed limitations. If the spider crab attempted the behavioral repertoire of a true king crab, rapid pursuit, forceful defense, aggressive interaction, the design would betray it almost immediately. Functionality exists, but only inside a narrow corridor of acceptable behavior. The resemblance becomes misleading, a visual promise of robustness that the biology never intended to fulfill. What persists is not strength, but compliance with constraint. The animal remains alive by never fully inhabiting the body it appears to have. Living a century on a slow biological burn. 100 years is an unreasonable demand for a crustacean. Joints wear, cells accumulate errors, environments shift, and energy budgets tighten with time. Longevity usually belongs to organisms with built-in buffers, thick tissues, redundant systems, or the ability to retreat into dormancy. The Japanese spider crab has none of these luxuries. It remains active, exposed, and metabolically engaged for decades, yet records and growth patterns suggest individuals can approach a century of life. The paradox is not extreme lifespan alone, but the method used to reach it. There is no pause button. Survival is achieved through sustained, low-intensity operation, a biological burn rate kept just above the minimum required to function. Metabolism runs slow, not because it is inefficient, but because any increase would destabilize the system. Energy intake from scavenging and opportunistic feeding barely exceeds maintenance costs. Growth, repair, and reproduction are carefully rationed. Nothing happens quickly enough to create heat, waste, or cascading failure. This strategy works only in environments that tolerate slowness. Cold, deep waters suppress reaction rates, lower oxygen demand, and reduce the frequency of encounters that would require rapid response. The crab does not conquer time. It avoids provoking it. Each year adds wear, but at a pace so gradual that repair can remain incremental rather than urgent. There is no dramatic aging curve, only a long, shallow descent that may never reach collapse before external factors intervene. The unsettling truth is how conditional this longevity is. A slight rise in temperature would accelerate metabolism. Increased activity would spike energy demand. Environmental instability would force faster decisions. Any of these shifts could push the system past its narrow operating window. The crab's lifespan is not evidence of resilience. It is evidence of how precisely its existence is matched to a stable, indifferent world. Living a century here is not about endurance. It is about never exceeding design limits, not once, for an entire human lifetime. The organism persists by staying boring, slow, and mechanically conservative, trusting that nothing will require it to change. In a universe governed by entropy, that trust feels misplaced. And yet, for now, the spider crab continues, not aging loudly, not failing dramatically, just burning time at a rate so low it almost feels like an accounting error that nature has not yet corrected.